this first session in the afternoon of our conference. And it's a great honor to introduce as our first speaker, Professor Karniadakis, who is now the Robinson and Barstow Professor of Applied Mathematics at Brown University. Professor Karniadakis is a very well recognized specialist of stochastic multiscale modeling, both in physics and in biology. And among very long list of recognition and awards, he is a fellow of SIAM, the Society for Industrial and Applied Math, a fellow of the American Physical Society, a fellow of the American Society of Mechanical Engineers, and an associate fellow of the American Institute of Aeronautics and Astronautics. And in addition, he received the Kleinman Award from SIAM, the Auden Medal, and the CFD Award from the US Association in Computational Mechanics. Thank you very much for agreeing to speak in the conference.
If you hear me, just share my screen, see if we can all see my screen.
Great.
Yeah.
So you can hear me and you can see my screen?
Yes.
Okay, great. So let me just start with this statement that I believe that machine learning and neural networks research is at the crossroads right now. In fact, I believe it is in a stagnation point, despite the hype and everything. I believe that we are at the stagnation point, trying to improve NIST and so on at 0.01%. The physics that I'm interested in, there are some advances and applications, but I don't see big ideas. And so just for example, today, you will probably see, according to projections, 200 papers published. For the week, there will be 1,000 papers. It's projected that there will be 100,000 papers on neural networks this year. And yet, the progress is very incremental. It is very incremental, that's my thesis, my opinion, that because we just don't exploit what is possible. What we have, all these papers deal is with a function approximation. You have data in, data out, you have a function, you try to approximate that. I think we know how to do that, and we also know the two big problems. The holy grail is backpropagation, and still an unsolved problem. And second is generalization. However, I submit that going to operators, approximating nonlinear, arbitrary nonlinear explicit and implicit operators, which would come from the calculus or non-calculus or fractional calculus, or no calculus at all, like for social networks. That will change this bottleneck. There will still lots of issues to be addressed, but I think it will be a new era. And earlier today, you saw my collaborator, Andrew Stewart, he talked about it, about learning operators. We started this work about 3 years ago. Lulu was a PhD student of mine now, he's at MIT. And we just got our paper accepted in Nature. It's more than 60 pages that has the theory and 16 different benchmarks from explicit operators to implicit operators, PDEs, multi-scale, multi-physics problems to choose from. So I'm going to tell you about this today. That's sort of the talk. But I want to put things in perspective and give some the spotlight on our previous work and how we thought about it. For many years, for 30 years, we are solving problems in this box. You know, the PDE is just like in every applied math. We pretend we know everything. We just have boundary conditions, and we develop the best methods, like spectral element methods, discontinuous Galerki methods, and so multi-grid methods, and so on. Now, we introduced about 5-6 years ago physics-informed learning, which is this middle category. The reason was that not to replace what we had with the solvers, but actually to solve realistic problems, problems which are not well posed, There's no always data on the boundary conditions. Problems for which you don't know the entire physics. In the reactive transport, you never know exactly non-equilibrium kinetics, intrinsic fluctuations, and so on. So that's sort of the physics-informed neural networks. And today, what I want to talk about is this DeepONet, which addresses this more difficult category, which is making sense from cases where you know very little, you just have data. Now, DeepONet, I should say, doesn't just belong to this box, it belongs to all these boxes. So the correct way to draw this would be DeepONet to encompass the small data, the sum data, and the big data regime, because we're trying to learn operators. So let me just tell you what DeepPins is in case that nobody has heard about it. But I know it's a very popular method because it's the most downloaded paper this year since it was published in JCP. And the idea is to bring data and physics together. So this is the data network here. This is the physics network, and we remove the tyranny of grid by going to automatic differentiation, and you can deal with any of these operators. Of course, every time you take a derivative, effectively, this computational graph, which is a nested computational graph, very difficult to visualize, so I put it in a box. Every time you take a derivative, this expands by a factor of 2. So if you start with 10 layers of neural network on the data side, then you have 20, 40, and so on for this case. So it's a really deep neural network. The PIN is a deep neural network that, of course, includes the data here, the mismatch in the data, and it penalizes residuals, boundary conditions, constraint monotonicity, thermodynamics, and so on. Now, there's more than 500 papers published on this topic, and every day more papers are published. Now, it's a very simple code. There's no sophistication here. It's as simple as it gets. This is something that the high school, even professors can program. In TensorFlow, you can just have a few lines of code. The important thing is that the X variable is not discretized, it's a continuous variable. Same thing for T. Data could be on the boundaries or not. For example, here there's a gap in the boundaries. And then you evaluate the residuals of all conservation laws and constraints inside, and you penalize them, then you're done. So in about 10 minutes, you get a solution. So now, a more interesting application of pin extension, there's many extensions, there's a whole alphabet now of pins for stochastic PDEs, fractional PDEs, and so on. But this one, it makes it really, really simple. It makes finite elements, I think, and all these other domain decomposition methods being obsolete. And here's, again, the Berger's equation, xt. This is now a flexible space-time decomposition. The dolphin is one neural network. The blue sea is another neural network. Not only you can do this simultaneously with 2 different neural networks and 2 different GPUs, but stitching together the solutions is very simple. You simply penalize the residual at this red line. Notice that one domain is this domain, a blue with a hole, and this, of course, domain has holes and so on. We don't need, unlike this continuous Galerkin and so on, flux-based method, we don't need to compute fluxes, therefore the domain can be arbitrary. So X-pin, extended pin, is really very flexible, and it's only one line compared to what we had before. So the 10 lines now of a full big code, 100,000 lines, become 11 lines. All this is captured in this DeepXD library, which is the most popular library, over than 70,000 downloads since it was put on GitHub. And also, if you look at the papers, I don't really pay attention to these things, but somebody told me that in JCP right now, number 1, number 3, number 8, number 9, number 14 is our papers from my group. The rest is actually from my students, Paris Perdikaris and other people who try to mimic using names like physics constraint and so on. And I just want to make another provocative statement that we call it physics informed and physics guided. Every time I see physics constraint, I get upset because I love physics. And physics is there to liberate us, not to constrain us. So please don't use physics constraint neural networks. The industry likes it, and I work with lots of industry and so on. So that's sort of a little propaganda for pins. But as I said, there's no sophistication here. We do have theory and so on. I'm not going to talk about this. Instead, I want to talk about from function to operator. It's not just image classification here, but we go from a finite dimensional space to another finite dimensional space. We're talking about operators which are explicit, like derivatives, integrals, collision operators, Laplace transforms, And then dynamical systems, the Navier-Stokes equations, chemistry, multi-physics systems, biological systems that we don't know with all the functionality, social systems for which we know no equations, or, and this is the context of the big wave now, right now, which will drive our economy, it's called digital twins. So digital twins consist of not just one systems, but systems of systems. And I think this black box, treating black boxes and system identification with these operators, arbitrary nonlinear operators, I think we can get there. Otherwise, I don't see any way to get that. So let's, what's the setup here? The setup is that we have a function or functions, u, and we have this map, the nonlinear operator that will map u to g of u of the output y, and I will make the output y continuous. So the output space will be continuous. So schematically, what you see here on the left is we train the network given all these functions, which will belong to some input space v. And then we ask the question, and then we observe the output. So here we have to have labels. Unfortunately, and that's a good thing, and I will explain why, we don't need to have a lot of data on the output. It turns out that it's better to characterize more accurately the input of than the output. But anyway, it could be multiple inputs. Then the question becomes, after you've learned this operator, you give me a new excitation, a new source term, new boundary conditions, functional boundary conditions. What is the answer and how fast you get it? The answer is you get that in 0.01 second on the laptop. So that's why you will see people get excited. They talk about 1,000 times. Our work shows that we can have 100,000 times speed up factors compared to standard CFD solvers. Now, how did I get into this? A few years ago, I was teaching a class and I asked myself, can I approximate functionals using neural networks? And I ran into this gem, this very nice paper. I don't have it here. It's 1993 paper by Chen and Chen. Chen is professor, Tipian Chen is professor in Fudan University. Recently, he wrote to me, he's at the age of 87, because nobody paid attention to his theorem. And now this theorem here is the counterpart of the Saipengo theorem for universal approximation for functions, but it is actually for operators. So let's read through it. So you have some continuity. You have a compact space V where you draw the input functions U, and then G is the nonlinear continuous operator. And basically the theorem says, all theorem, as you can see, at the same time as all the excitement on the theoretical side was taking place in the early 90s and mid 90s, that the G of U of Y, the operator in the Y, can be approximately arbitrarily accurately with epsilon very small. Now, if you look carefully here, there's a double summation. There's two sigmas, which indicates that there are two neural networks. And indeed, there's this neural network here where my cursor is, if you can see it. That's the trunk. That's the output. The Y now becomes a neural network. The output space becomes a neural network. So that's what the theory says. Because I've seen other implementations, and that's not the case. The input itself is this neural network is separated at the output. So you have two neural networks that work in sync in order to give you the output. And a couple of months ago, I was giving a talk at Tommaso Poggio's center at the Center of Brains, Machines and Minds and Machines. And he said, somebody said there that this is how the brain works. I don't know anything about the brain, but this is how we implemented this. The math actually suggests this one layer thing suggests what to do. So if you take, let's start with the output. This is the trunk. This is the output here space. It's a continuous space. So P here, for example, would be the width of the neural network of a single layer. Okay. Now to synchronize it, you have to reduce also this other network, the input network, which you observe the input U at M sensors. We call them sensors. But there are different ways, of course, to represent this. Could be a neural network itself. But anyway, you can see here, that's the input. This is the output. We cross them. N is the number of neurons in the branch. P is the number of, you can think of a number of neurons or the approximation, Fourier nodes, whatever you want, modes in the trunk and so on. So this, in other words, this theorem here has a direct implementation that Lulu introduced to us and then tested. There could be different This one is sort of many neural networks, narrower, as opposed to concatenating the entire input and put it here in one neural network and so on. But let's stay with this. And then the question, do you need bias, unbiased, and so on? There are all these questions. I want to take some time to talk about the theory. Usually I don't talk about theory, but we have some theory now that it's very useful. First, to prove, which is in this paper I mentioned, an extension theorem that takes the one layer to a deep neural network. So this is a theorem that Andy Zhang recently, my former student, proved. So basically, you replace this network in the branch with a deep neural network, and the network in the trunk, the output, with another deep neural network. So that's sort of the extension to the Chen and Chen theorem. And I want to give you a sketch of constructive type of proof for this. So just to get some insights from this. So again, you're trying to approximate this operator in the continuous field output domain Y. So Y is in K2. K2 could be arbitrary, but we can extend it to this. So think of K as this arbitrary contour, but we can continuously extend it and embed it in this canonical domain, and therefore I can do like orthogonal expansions, for example. So that's what we do here. First we do a piecewise interpolation, then we continuously extend this approximation to the domain D, the square, let's say. Ek of Y here will be some orthonormal basis in this new output space here. K2 is a space, as I said, so we do a spectral expansion. Then we do an interpolation for this part. Now interpolation in the Y domain, right? So with some neural network. And then we do the neural network approximation. As you can see, N here approximates that. Chi here is an indicator function. Of course, you can take the integral here in Y, so that's just a coefficient. We still have this basis. So if you look at this and you compare with the original approximation expansion, you see that's the outer loop. This is the inner loop of the approximation. So basically, we want to see that if this here, G, can be approximated by a universal function approximation for function, and also this EKY, this is just a coefficient, EKY would be basically the neural network we approximate for the trunk. Indeed, given the continuity requirements that we have, the compactness of the space, we can use the Pengo approximation theory for function constructively to show that indeed what Chen and Chen propose is a very good network. Now, how do you go to the error estimates from there? Well, we need to show that, in fact, in every case we have in the paper, I mentioned 16 of them, we prove that G is Holder continuous. And here's the definition for alpha less than 1. Of course, if it's Lipschitz continuous, like this big class of advection reaction equations, or this other one, hyperbolic scalar conservation laws, then that satisfies the continuity. So we need Holder continuity in order to come up with error estimates. So this is an area which I would invite a lot of people to work on, because I think a lot can be done. Here I will give you some small samples of what we have done so far. Let's say G is a linear operator, like an integral and so on. And then the approximation error is, you can use a ReLU network, so you can eliminate the error in the branch. So basically, the whole error becomes error in the trunk, and you can see here an error estimate. 1 over P. P is again you can think of this as Fourier modes, or you can think of the neural net of the neurons in the trunk. M is the number of sensors that you use to observe the input, and this trunk here is related. This is the number of neurons. This is the layers of the trunk. So everything is there. Now, how do you prove this? This is fairly easy if we start from what I was before, this expansion here, because U now is constant, approximate accurately. You can bring it out here, and then you really need to approximate just the trunk, as I said. Of course, you have universal approximation theorem, so it's easy. What happens if you have a nonlinear operator? And here's an example. We have, I talked about conservation laws. Here I have the Berger's equation, but actually any equation that can be reduced to a linear equation, like all the integrable forms, KdV and all this, the whole models, all this can be treated the same way. But this is just a Berger's equation. The function input here, we pretend that, or we assume, it's the initial conditions, which I observe at m points, let's say in this simple representation. So the theorem that we have is that in the L infinity norm, we can find a bound from above, as you can see, in terms of the number of sensors, the width of the neural network in the trunk, in the branch. And then the all important term is this one here that mixes the input and the branch, in the branch. And that is 1 over square root of m. M is the number of points again. Now, I will show you how we get to this, but before that, we have a theorem that shows that if you don't assume something about the conservation law, for example, that you're looking at, then the error estimate cannot be as good. In fact, you see a term here that diverges in the branch. Unless you make an additional assumption, this term, and as I said, this is our theoretical bottleneck. Some of you, Jin Chao, I know, is a very smart guy. He can come in and crack it big time. Let me show you how we do the Berger's equation. So Berger's equation, all these integrable forms, can be written in terms of this ratio using the Kohl-Hopf transformation. So K or kappa, whatever, that's the kernel, this exponential kernel. B is this other kernel. So we know that these are exact solutions of the Berger's equation, right? Now, if you can approximate with rational polynomials, V, for example, and then you can reduce these U of X. Now, remember what U of X is actually the output, is the mapping, is G of the initial conditions for the output. So that's the map. So U of X now can be approximated by a rational, by polynomials and the rational polynomials. Okay, so it's sort of a rational function. So this one can be approximated by rational polynomials using ReLU networks, for which there's a theorem which you can utilize, and therefore this rational approximation of the output could be written in terms of the neural network plus order 1 over m. Okay, so that's an upper bound, pessimistic upper bound, but it's a good one. The proof of that, again, now if we go back to prove the error estimate, you can see if you plug in what I had before, if you plug in, after you take the Fourier transform, let's say, and I assume periodic boundary conditions, if you plug in the residual here, then you do the interpolation, you come up with all these terms that I have here. So in summary, what we do, we approximate EK, the orthogonal basis, by a trunk net, and then we have this rational approximation. As long as you can do a rational approximation, and I said all the integrable forms you can do it, then you can come up with a similar estimate or better. And the key idea is, again, to start with this Kohl-Hopf transformation, and then you can extend it these other cases with and so on. Now, one of the questions, and so far I use a 1 over m type accuracy for the inputs, but there are many different ways to represent the input space V. A simple one here, I show you just a very simple one for assuming that you're looking at this equation here, this map. So if you sample equidistantly U from the real function, and you use a space like a Gaussian process, then you can come up with a bound that I show here, where this kappa, the constant, would be 1 over m squared, not 1 over m. And then most importantly, because people are talking about discretizations and all this other nonsense, most importantly, you can bring in the correlation length that characterizes the training right in the L square. So now, one caveat here is that the theorem actually, and I was talking to some people who tried to say, oh, this theorem is not good. The V is a compact space. It turns out that V is a compact space, of course, for the theory. For the experiments, you can have, that's why I will show you a Laplace transform. It doesn't have to be a compact space. And here we use actually a Gaussian random field, which does not satisfy this compactness. But anyway, the theorem that we have, a more refined version of this, is that in this case, where we have the input space given by a GRF, you have a bound like this, C times kappa, and kappa, as I said, is 1 over m squared, L squared. So this is now associated with the input space, the fact that you take a function U, but of course, importantly, you can use a neural network to approximate U. You can use a wavelet expansion or spectral expansion to approximate U. And I'll show you some examples later. So where are we now? We are basically going back to what I said, the problem setup. Let's look at panel B. we have functions as inputs u, which you observe at points, and then we observe the g of u at some point, not a lot of points, and then we train this neural network, the branch and the trunk, which they work synergistically. That's very, and in sync, and that's very important. So let's do the very simple pedagogical example. First, let's learn this integral. I want to map the integrand u of t to an integral s of x. The domain of the output will be 0 to x, or it could be actually 0 to infinity, as I said in the Laplace transform. I'll show you in a second. So we take 10,000 functions u. We observe them only at one point. In other words, s at one point in this interval, or interval from 0 to infinity. So by doing that, we learn g. And you can see here the mean square error for the training and the testing is basically on top of each other for our network. In other words, the generalization error, as I show here on the right, for one of our best networks, the one that I show on the right, which on the before on we call unstacked DeepONet, as there's very small this gap in neural network the generalization error. If you use FNN, if you use ResNet and so on, you see the generalization error is much bigger. Not that you cannot do it, just that it's not so flexible in terms of having arbitrary points. In DeepONets, you can have arbitrary points in the input, arbitrary points in the output. Now, what happens when you only train at one characteristic length? In other words, when your space V, instead of training across different correlation lengths L, you only train, you're lazy, and you train only at a very large correlation length. And somebody gives you a function which is outside totally that GRF space. Well, so L is 0.5 here. We're trying to find the error. The error will be big. But here we show what happens if you choose your input space judiciously. For example, if you train only at L 0.1, right, and you give me that function, you can see the error will be less than close to 1%. If you make the network bigger, it will be even bigger and so on. Now, if I train the network at 0.1, 0.5, which is here, and I try to predict something outside the distribution, the error will be 10%. So you have to be careful how you choose the input space. Those people who talk about operator regression haven't really carefully considered this. It says, okay, voila, we did it. It's not like that. And we fail many, many times. Now, there may be cases where, and I can always break this. I give you a function which is really, really outside, very far from what you did. Now, in that case, that you can combine it with PIN, so you use transfer learning, in other words, basically by allowing the trunk, a few layers of the trunk to be free, you can use pins, and it's just 10 iterations, you can nail the answer. Or if you have data, you can use supervised learning. I will give you an example later of how you do that. I talked about Laplace transform, just to show you that the accuracy is very good. In fact, we can extrapolate. This is a case where we train at 0.1, and we extrapolate a smaller correlation length. Again, GRF, which violates the theorem, gets the accuracy is very good. This was done, by the way, by a student that I never met. It's an Indian student from far away. It's supervised by Lulu and me. So he is an undergraduate student. He did that for his project. Now, one of the surprises that we encounter with DeepONet is that it's learning exponentially fast. Take this example here. This is an interesting example because we have one excitation for one of the pendulum. The pendulum is coupled to the other pendulum. And what we see here, let's look at the middle panel. We see that the mean square error versus the training data decays exponentially fast. Decays exponentially fast, and I've never seen this in any neural network, until some point where it saturates and go back to Monte Carlo sampling. Now, we haven't designed the perfect neural network, so we increase the size of the neural network, just the width, and you can see this transition point moves to the right. If you string it, the transition points from exponential convergence to algebraic convergence moves to the left. And in fact, we observe that to every different application we did. So it seems that there is hope that we can actually learn very fast, even problems at scale, because one can balance data. And I think it's a matter of how do you balance data with a network. Another holy grail in machine learning But that's sort of a deeper philosophical question. We apply this to a diffusion reaction system. For example, this one now, you are in X and T. Here, what I have is I show you the random points where I measure the solution. Now, here, I don't need the PDE, right? I don't need the PDE. I just need the PDE to generate data. But if you give me measurements in this time-space domain, this type of measurements, I can actually learn the operator, and you can see the testing error. When you have enough functions and you have enough points, P is the number of locations here, then you have like 1,000 points, not a lot, 1,000 points. You can basically learn, you can see the generalization error is 0. You can learn really, really interesting operators. My favorite operators are the fractional operators, as some of you know. So for example, if I want to learn the Caputo derivative or any fractional operator, I can just use the formulas of the shell formulas and train with lots of functions. Here's the workflow, and basically learn this. Now, the reason I show you, so the Caputo derivative, for those of you who don't know what this is, you should, but it's a lot of fun actually. It's not a Riemann-Liouville. Here the derivative goes inside the integral, but it's just this singular integral basically to learn. The reason I show you this is not to show you another integration, it's to show you that how important is the input space V. For example, before I use GRF, and you can see the error here with the green line and the testing and there's a little bit of generalization gap here. Now, if I use something I developed, which we call polyfractonomials or even Legendre expansions, you can see representing spectrally the space, the input space V, the error decreases by 2 orders of magnitude. Okay, so that's really, really important. It's important when you try to learn really complex objects like a fractional Laplacian on a disk, a bounded domain, which is difficult. It's not Fourier. This is really difficult. So now in this case, we have the best representation of the input on a disk. For those of you who know what the Zernike polynomials are, basically Jacobi polynomials orthonormalized on a disk. The guy who found them, Zernike, was an experimentalist doing microscopy and developing lenses and so on. But you can see here again, if you the importance of the space. I also wanted to say that DePauw-net, in this case, if the domain is simple, something like a convolutional neural network which has some structure could even help and even beat DePauw-net. And here I have an example where CNN actually, if you are able to organize the data to use it as an image, then CNN and this representation of the input can give even better results. You can learn stochastic operators. Here I show you dy dt minus k, ky or ky. K is a process, not a random number, which you can represent with a Karhuin-Loev given some correlation length. We haven't done yet the white noise case. So I'm talking about color noise where you can truncate the expansions. So these are now will look like a high dimensional input spaces for the branch and the trunk. We have n+1 domains here, spaces. And in fact, you can find that you can learn the stochastic operator, the stochastic ODE with extremely good accuracy, and you can even track trajectories, as you can see here. You can do that. Okay, now some math behind it. As I said, to do the estimates and justify this, you have to show that Dios operator is Holder continuous. In this case, a stochastic ODE, it's fairly trivial to show that. And of course, you need this because here you have the approximation theorem. I told you, but here you need the to have the Holder continuous. So in this case, you can find exactly the solution. You can write in the closed form, and then you can use some inequalities to prove that indeed the G operator is Holder continuous. For the fractional case, we also have that in the paper, in the long paper I mentioned. You can extend this to stochastic PDEs. And here again, this is what we use in uncertainty quantification. B will be now expanded like Karhuin-Loev. Again, this is a 6-dimensional space, not very small correlation length 1 to 2. And you can get a good standard deviation, you can get good statistics, but also you can get good trajectories if you use the same seeds. I want to finish here with some applications, real applications. This is a multi-scale operator we're building now. growing bubbles. Bubbles, you can grow bubbles in many different ways. Here, we could use a video as an input. In fact, as I told you, CNN could be an input to the branch of a video or images, snapshots. But here we generate data from an equation that's called the Rayleigh-Plessé equation from Lord Rayleigh. It's a nonlinear equation. It can give you, given the pressure between the bubble and the outside, the ambient, you can predict the radius. So that pressure difference is the input to the branch. The time is the output. So this is like a functional, actually. It's not a full field. It's just. But I want to show you the multi-rate character of this problem. I draw a lot of arbitrary distributions of pressure, and the effect of that is the radius. The bubble breathes, it oscillates very fast, and then because of dissipation, there's viscosity, it decays. So there's truly multi-rate dynamics. And here you can see, compared to CFD or the exact solutions, the orange line is on top of the blue, which means that we can capture with relatively small training, you can capture very quickly this and predict this in 0.1 second. Now, one of our reviewers in the Nature paper asked, how about LSTM or sequence to sequence and so on? So here I have a comparison of LSTM. Let's look at the first column. If I use 20 points per trajectory, notice what happens to an LSTM. Notice what happens to DeepONet. With only a few points, 20 points per this trajectory, this multi-rate trajectory. Obviously some sapling, right? Because look how many oscillations you have. Obviously way below Nyquist frequency, but you have a lot of trajectories of them. LSTM cannot deliver, DeepONet can totally replace LSTM. DeepONet can work with stochastic data. Here we do some molecular dynamics. So you can see this bubble, it oscillates, it has fluctuations. So again, we can learn the data now is from molecular dynamics. The previous data was continuum. So by inputting data to this black box DeepONet operator, I can have a multi-scale operator for the bubble. I want to show you this example. Here is, we just delivered this to, we're about to deliver this to Sandia. It's a flapping airfoil. The angle of attack is given. You know how you fly through, but you want to know all the forces on the body. You want to do it at 0.1 second or faster. We'll train this, as I said. Notice here, instead of a time in the input, I put the history. So I totally replace LSTM or any of these recurrent type neural network with DeepONet. We have extremely good accuracy into the future, outside the domain of training. But I want to show you the pressure distribution here as a function of time and space around the airfoil. And if you look at this 0.1 down here, every point on the airfoil has a different signature. 150 points of them. We track them, we train them, and you can get very high accuracy. In fact, the vorticity, which is very difficult to track, especially where you have competing dynamics with multi-frequencies, as you can see here in the back of the domain. These are real applications. These are not Mickey Mouse signs of 2x and so on problems. Okay, this is something that my colleague Qinwan Xu was doing, published a paper in WENO a couple of years ago at JCP. This is a difficult case because we're talking about chemistry, non-equilibrium, Riemann problems. So what we did here, the input function is the initial Riemann problem, okay? So the smoothness of that will give you a myriad of solutions. So what we do here, the chemistry, we have 3 different species. So we use 100 trajectories only 100 trajectories for training, 50 trajectories. So my V space is 100, 50 trajectories for testing. And then given the chemistry and the initial conditions for velocity and temperature, I can predict the future. And I use a DeepONet for each one of these. So DeepONet is an operator for the N2, oxygen, O, velocity or temperature. Then independently I can obtain this. I contain it with a very high accuracy here. You can see 10 to the minus 5. I start with a black line. You can see you have expansions, so you have shocks, you have all the discontinuities at different points, and the results are indistinguishable, solving the Euler equations. Now, even for this simple 1D problem, because of the chemistry, the time step in WENO is extremely small, 10 to the minus 8. Here I compute this in 0.01 second or something like that. Now we'll finish with this example. It's a true multiphysics problem. This is something that DARPA reported recently to Undersecretary of Defense, because we're able to solve this problem 100,000 times faster than CFD codes. It's still 1D problem because we just look at the boundary layer here behind the shock. It's full Navier-Stokes with 5 species now. So what we do here, we will input the temperature and the velocity, and then in the branch, and we predict the output in steady state, in this case, for all the chemistry. Chemistry, as I said, is very difficult. But we can do the opposite. We could also start from a chemistry and find the corresponding velocity, because we learn these depot nets for the velocity, for temperature, for every one of these species. This problem is not trivial at all, the Mach number 8 to 10. The species go from 0 to 8 orders of magnitude bigger, okay? And the Mach number is 10 to 8, 8 to 10, we can go to 13 outside the range and so on. And here I want to show you how accurate we predict. And here we actually solve the real problem. The real problem is you fly one of these hypersonic cruise missiles and you have some measurement. The only measurement you have 0 measurement in chemistry. And you have no time to run WINO. The only measurement you have is the velocity and the temperature. Some measurement, 3, 4, 5 measurements. So now we have this deep M&M, a supervising neural network, which is built based on depot nets. The depot nets is basically plug and play, modular building of the whole hypersonics problem. Any multi-physics problem, multi-scale problem can be like that. So you can see here, given U and T, we can predict the chemistry. The chemistry may not be correct, so then we have to see, to compare it with what the output of these operators is, U prime and T prime. Now, remember, I have data on U and T, so I will compare here. I also, in my total loss, I will now have a new term. Remember in the pin, I had the physics. Here, I have a term on the operator level. So I penalize the operator. Of course, you can regularize or not. That depends on the problem. Bottom line is, with only 4 points, you can predict a new situation very accurately. You can predict with a 10 to the minus 5 accuracy compared to this CFD solver, but you're 50,000 times faster in this 1D problem. Depot nets and deep M&M is just exactly, it takes a few iterations because you don't have a lot of data to do this, but deep M&M gives you a good initial start. So let me just summarize, summarize what I said. Basically, I want everybody to remember this neural network. And I think you can all expand to it. You can be more sophisticated, like pins. I get all these papers now about pins, how this guy wrote a paper where he can beat my paper and be faster 11,000 times. And I used to get upset with these things. Now I bless them. I bless them that they promote this stuff and create new science, and that's what it's all about. So let me just say that you have a branch for the input. You can have multiple inputs, multiple outputs. Here, I use the coordinate output, but also I use the history sometimes just to emulate and totally replace LSTM and RNN and all this. But I will also, you want to use this to tell you how we wrote this paper for 3 years in the making. We put the paper in the archive a year and a half ago. We just got the paper accepted in Nature. And to do this, the input was very big. So we had a collaborator and former student, Andy Zank. He was working on the theory. That's an input. And then we had Lulu, who conceived this, and basically the contribution of those 2 people, as a lot of other people contributed to this. Finally, I want to acknowledge the Film Center. I proposed this 5 years ago. People didn't want to hear about physics-informed learning. I'm writing an invited paper by Nature on physics-informed learning. For those of you who are not believers, physicists are interested. So you'll see soon a paper on physics-informed learning. We'll have some of your papers in there. And also I want to acknowledge the new MURI that I have with the good people from Caltech and Stanford and University of Utah on pins and physics-informed networks, not just physics-informed neural networks, but learning and meta learning. So with that, I want to thank the organizers, Chinchao Xu, my old friend and good collaborator, and everyone who's listening. Thank you very much.
Thank you very much.
Really.
We have had many questions both in the chat and in the Q&A. So maybe we should go over those. I will read them and then George, you can answer them. So let me go in reverse order. Let me start with the chat. So first question is, on the slide with the convergence versus number of samples for the gravity pendulum case, how do you scale the number of training samples in U versus the number of training samples in Y? So the sample function evaluations.
Oh, yes, that's a good point. I mentioned that, and this is observation that of course, we know the inputs, right? So we can use a lot of points there, and or as I said, you can use spectral expansions or a neural network. So there, we want to put as much accuracy as possible. In the output, of course, you want to do that, but you know, we know, I work with and I work with experimental, so I know how much 1 point costs. so we want to use very few points. So we actually use very few points in the pendulum, for the pendulum. So maybe just a couple of points, depends on how big the domain is. So I cannot answer that question unless I give you the specifics. We have tables in the appendix of the paper. You will see all that. The archival paper doesn't have all the details, but as I said, there's 60 papers in the Nature paper. And so all these details are there.
There's a follow-up to the question, which is, does one need to increase both at the same time to observe the initial exponential convergence?
Yeah, yes, there's a good point. In fact, the advection, well, first of all, to remove the, to bridge the gap between training and testing, and I showed that for the diffusion reaction, but also for that problem, I didn't show the results here. We also observe exponential convergence even for the PDE. And yes, the answer is yes, you have to balance it. You have also to balance with the size of the network. That's what I was trying to tell you. So that's right now, I don't have a priori a way to do it. So that's kind of really empirical. And also there's some anomalies, like you could see, yes, it is an exponential convergence, but the exponent is not that great. So although you reduce eventually to really bad sampling, but the answer is yes, you need to have balance now.
Right. A more general question, which is, can you reiterate the improvements in computation time for PIN?
Oh, look, pins. If you start from scratch, pins are expensive, right? If I, for example, I was solving a solid mechanics problem, and like finding doing a stress concentration around the hole, it takes 10 seconds with abacus, okay? And it takes an hour with pins for the forward problem. Now let's solve the inverse problem. Where is the hole? If I give you a displacement, where is the hole? It takes a year with abacus. It takes an hour with pins, because exactly the same problem is exactly that. So now. Pins alone are expensive the first time. Of course, we're using transfer learning and so on. That's why I think going from pins to DeepONets and back to pins is a good workflow. So DeepONets can generalize what pins can do, or any other method for that matter. You can use pins and you can use finite elements, and no data is left behind in DeepONet. Then you use pins at the very end if you know the equations, and then there you only need 10 iterations. That's very fast. It's still, and I show you that at the end, right? It's still 0.01 seconds to predict. But pins, raw pins are expensive, the forward problem, not the inverse. Yes, good question.
All right, let me go a little bit to the Q&A now. Again, from last to first. DeepONet can replace LSTM. I am curious to know if it can replace for all applications or just for high dimensional applications.
Oh, I mean, it's hard to argue, but I have to tell you, when we started this, we were not sure. And now different people, very creative people around me and far away in India and other places are playing with DeepONets, and we see surprising results. I don't know yet. I don't know. Earlier today, I attended a talk on interpretability and see what's going on inside DeepONet and take some X-rays. But the results so far have been surprisingly good. Sometimes you need to, like for example, to get a better accuracy, we put a history of the quantity that you predict, like LSTM. But then if you are in space, like this pressure coefficient, we normalize with the average. So it's like you know how we predict in CFD and mechanics, we predict increments from some previous state is better than. So if you put that as a coordinate in the output space and you make that continuous out space, things will work really well. That's my observation so far from my collaborators' findings.
Mm-hmm. Thank you. Still more questions, but we have time. Would DeepONet work on any kind of PDE, or are the limitations, or I guess, what are the limitations, for example, high order derivatives, etc.?
No, it doesn't matter. I mean, it doesn't have to be a PDE, right? It can be data. It could be, as I said, in this case, no data is left behind. Any data you give me, like I said, that's why I wanted to show you this example. In the DeepONet, part of it, I will input continuum case. The other one will be molecular dynamics data. Then I built this multi-scale operator. So I tell my collaborators, because I work on this problem for a long time, no more handshaking. It will be a one seamless multi-scale operator. And that's what I'm after. Now, it's not as easy as it sounds because you have to scale it, because you go from nano to meters, right? So you have to scale it. You have to use different loss functions. Like, for example, one loss function would not work. You have to do meta learning of the loss functions. You have to use MAE instead of MSE. You have to use relative MAE because of the numbers, which are very, very different in the scales. But it doesn't really matter how you have data. So no limit. Lulu is on the call here. Lulu, do you think of any limitations? Because I want to be fair, but I haven't.
So theoretically, we require the mapping from the, let's say, the input to the solution to be continuous operator. But in practice, we also saw, even if we break this assumption, DeepONet still works, for example, the shock problem and a few other problems.
And also the compact space, I said that if you don't have compact space, you cannot do of course, the universal approximation theorems, but most of our applications are not, is GRF and Laplace transforms and other things. Yeah.
Let me skip one question because there's one that is a little bit related, so you might want to. The operator approximation theorems assumes that the domain of the operator is some continuous functions, but in condensed matter physics, usually the domain of operator is not in continuous functions. There are singularities there. Is there any such result for operator whose domain also includes functions with singularity?
Oh, that's a good question. Apart from the Riemann problem, I don't think we have anything like that. We have a case, we publish a case where we go through a bifurcation. So we have an electroconvection problem. At low potentials in the channel, you have no flow. Just like the thing of just a conduction, right? But it's electricity. Then at some point you change the bifurcation parameter, then you have flow all of a sudden. So we go from zero flow to flow. So I could capture that. I see here that Chris Schwab, hi Chris, broadcasted that he has solved this problem. That's what I said. There are smart people, smarter people than me around the world, and Chris has been always there to solve the problems I cannot do. So this is another one of these. Thanks, Chris.
Thank you. There's been let me go back to the one question at the end. Sir, what would you suggest to capture very high shock values of a function in a very, very short time when solving a PDE?
Can you repeat, Pierre? I didn't.
What would you suggest to capture very high shock values of a function in a very, very short time when solving a PDE? I'm not quite sure what is.
Lots of data, maybe. I don't know. Maybe map it. I mean, actually, here's one thing that is a very good question. It turns out that, and this is also for pins, right? Pins will fail if you have stiff problems and so on, and everybody writes lots of papers on that. I show you how you can use XPin. But it turns out that you can use manifold learning, or you can use just take a old good conformal mapping to take like you have let's say you're looking at the concentration of stresses in a hole in a big domain. That's a very difficult problem. pins will totally fail. Well, do the transformation, capital R is 1 over R square, and then you bring the whole outside, and you can solve that with very, very few points. The same thing, so a transformation like that, that goes probably back also to the singularity that the reader asked. If you can transform it back with a simple transform, conformal mapping or other types of transform, and I think you have better chance of learning it. There is about the stiffness problems, partition of unity works. Chai Wei has written a paper on it. The people at Sandia, Nat Trask is making some headways on this with partition of unity for this type of problems. Yeah.
Thank you. Still 3 questions to go.
Okay.
What are the advantages of this DeepONet over polynomial chaos expansion for solving parametric problems?
Oh, is that the same question?
No, but it's.
I use polynomial chaos in some other papers that on doing the uncertainty for parameters, but I didn't present it here. Here, in the stochastic problem, I just represented my input, stochastic inputs like conductivities using a Carhu-Loev, assuming very generous correlation length, so I don't have 100 dimensions and so on. So yeah, I mean, all these other tools, polynomial chaos or whatever, you can bring it in. It depends on what context. As I said, white noise, I don't think you can do that. We work on this stuff for 25 years now on polynomial chaos, but it can be used. That's not the whole story in uncertainty in neural networks. We write lots of papers on that. Our latest paper on Bayesian neural networks. So it's not really, DeepONet is separate from a different concept than it's how you represent the input spaces, really.
Another question, which is, if we change the automatic derivative with finite difference definitions, will the method still work effectively?
Sorry, I missed that again.
Yeah, if we change the automatic derivative with finite difference definitions, will the method still work effectively?
Yeah, it works, sure, of course. I mean, Eric Darb is using some sort of a hybrid method, so he combines the best of 2 worlds. If you can have a neural network where you need it, and then you can use your finite elements, good fast solvers where you, especially for forward problems, makes sense. For inverse problems also makes sense. It depends on your, now, if you ask me, would I do it? I mean, CNN does that, right? You finite differences, so to speak. So I like automatic differentiation. I like to develop automatic integration, as I show you. So but like in fractional PDEs, that's exactly what I do in fractional PDEs. I see John Harlem asked me a question. In fractional PDEs, I use the finite difference formulas. Or we use variational, which I didn't talk about here, but yes, I can use that formula.
Can I say a quick word here?
Sure.
Yeah. So just just following up on what George was saying. So actually, in our work, it's not really a deep neural network versus finite difference. It's just that the question is, what do you use a neural network for? Like, what is the function that you're representing using a neural network? So in George's presentation, essentially the solution of the PDE was represented using a neural network, whereas, for example, in the work he was mentioning that my group is doing, it's more looking at constitutive relations or other unknown functions in the PDE that are discretized or represented using a neural network. So maybe this is the question the person was asking or not. So it's not finite difference versus neural network. It's just representing different quantities using neural networks.
If you have the problem, can you just do finite difference? Yeah, people have done it. I mean, that's not a big deal.
Yeah, there is also that too.
Okay.
Any more questions?
I think we should stop here with the questions because it's almost time. And thank you again.
Okay, thank you. Yeah, thank you.
Thank you, George.
Thank you.